Hello and welcome back. So this video is for class 12th and we will continue with the chapter ray optics. So previously we saw the derivation for the lens maker's formula, and as I told you before that derivation is very important and the formula is also very important. Now there is one more formula that you can derive from it, and that is called as the lens formula. Now already we know, so we will not go for the derivation, we just do a quick revision. So what is the lens formula? Lens formula is 1 by f equals 1 by v minus 1 by u. Of course we know f stands for the focal length, v stands for the image distance, and u stands for the object distance. So this particular formula is applicable for any kind of lens, for concave as well as convex. Similarly, now this is the lens formula. We also have a formula for the magnification by the lens, and that magnification formula is given by m equal to h dash by h. H dash being height of image and h being the height of object, which is also equal to v upon u. Once again, v is the image distance and u is the object distance. Fine. So these formula you should remember. Some basic numericals may be asked on them. Another formula you will remember is the formula for power of a lens. Okay, so power of a lens, P is given by 1 by f. So P is equal to 1 by f, that is reciprocal of focal length. Now SI unit of focal length is meters, therefore SI unit of power is diopters. Okay, which is denoted by the capital D. Remember, when focal length will be measured in meters, only then power will be measured in diopters. Next, we will see a formula for when lenses are kept in contact. Okay, so of course these formula are applicable whether they are in contact or whether they are very near to each other. So we have two, here we have considered two convex lenses. Again, this will be applicable for concave or convex, any type of lenses. So we are having two lenses. This lens has got a focal length f1, the other has a focal length f2. They are placed in contact with each other. Now any ray of light that is coming in will get refracted by f1 and then get refracted by f2, and then we'll get a final image being formed. Okay, so this lens, this combination is going to have a combined focal length, right? So we are going to see a formula for that combined focal length, which is very easy. So because of these two lenses, the combined focal length f will be given by 1 by f is equal to 1 by f1 plus 1 by f2. Again, very simple formula. The reciprocal of the combined focal length will be equal to the sum of the reciprocals of the individual focal lengths. If you are having n number of lenses like this, the formula will be 1 by f1 plus 1 by f2 up till 1 by fn. Correct. Wherever the lens is convex, here we will get plus f. Okay, wherever we are having concave, this plus will get replaced by minus. Okay, that is the formula. And obviously now, since this is the focal 1 by focal length, this can be called as power. So the total power will be P, which will be equal to P1 plus P2 up till Pn. Right? P1 will be 1 by f1, P2 will be 1 by f2, so on and so forth. Right? So when we are having lenses in contact with each other, combination of lenses, these are the formulae for focal length and power. Now what will happen to their magnification? If magnification due to lens 1 is m1 and magnification due to second is m2, the combined magnification m will be equal to m1 multiplied by m2. So magnification will be a product of the individual magnifications. N lenses you are having, then it will be m1 into m2 up to mn. Correct? So these three formulae also you will remember for combination of lenses. Now we are going to see refraction by a prism. So here you see we have a cross section of a prism ABC. Right. This is ray PQ which is incident on it. Then it gets refracted. QR is a refracted ray, and then it emerges. RS is the emergent ray. Now I have tried to keep the nomenclature very similar to the one in the textbook so that you don't have any confusion. Then we have drawn normals at Q and R. Correct? The normals will intersect at the point N. Then the angle that is RQN we have named as R1, and then QRN we have named as R2. Okay, so this is the situation. Now we want to derive a formula for the angle of deviation. Now what is angle of deviation? See, PQ, this is our incident ray. So this incident ray is actually moving along this dotted line here, correct? But because of the prism, it gets bent to QR and then it gets bent to RS. So finally the ray goes to RS. So you can see there is an angle between the ray PQ and the ray RS. That is between incident ray and the emergent ray. There is an angle, and that angle is called as delta, angle of deviation. Okay. So remember, what is angle of deviation? The angle between incident ray and emergent ray is known as angle of deviation. And why the deviation took place? The deviation took place because of the prism. Fine. So now let us do the derivation. Very simple geometry formula we are going to use, so pay attention. So now, of course, this capital A, that is the angle of the prism, correct? When BC is the base, A we call as the angle of the prism. Generally, we are having equilateral prisms where angle of prism is 60 degrees, okay? So, when you look at the quadrilateral A, Q, N, R, we can see that opposite angles, they should come to 180. Therefore, you can see angle A plus angle N should be equal to 180, right? This is, I think, very easy to understand. Similarly, when you look at this triangle NQR, all the angles of the triangle, they should also, the sum should be equal to 180. Which are the angles then? R1, R2 and N. So you can see R1 plus R2 plus angle N is also equal to 180. So comparing these two equations, what can you say? You can see that A plus N is 180, then R1 plus R2 plus N is 180. That will mean angle A is equal to angle R1 plus R2. So let us write that. So we see that therefore A is equal to R1 plus R2. Let us call it our first equation. Now moving on. You will see for this triangle Q, let us give this a name M. Okay, so QMR, this delta is an exterior angle. So by using exterior angle theorem, you can see this delta will be equal to this angle MQR plus angle MRQ, right? So and how much is this angle? That is MQR. This will be angle of incidence minus R1, right? And how much would MRQ be? That would be angle of emergence minus R2. So for this triangle, using exterior angle theorem, we can say that, I will continue here, we can say delta is equal to this angle plus this angle. How much is MQR? That will be equal to incidence minus R1 plus how much is this angle? That will be emergence minus R2, correct? And then of course we can rearrange and we can write therefore delta is equal to I plus E minus R1 plus R2. But you can see from equation 1, R1 plus R2 that is equal to A. So we can write therefore delta is equal to I plus E minus A. Let us call this equation as our second equation, correct? So these are the cases we are seeing now. Now you will see that as you go on increasing the angle of incidence, the angle of deviation will go on decreasing, correct? It will reach a minimum value and again it will go on increasing. So there is a value where the angle of deviation comes to minimum. That is called as the angle of minimum deviation, dm. And when this delta is equal to dm, so when the angle of deviation is equal to dm, that is the minimum angle of deviation, this will happen when the angle of incidence is equal to angle of emergence. So this angle I should also be equal to E. And when this is happening, another thing that would happen is this R1 will be equal to R2. So basically this ray QR becomes parallel to the base BC. Okay. So when delta is equal to dm, I is equal to E, R1 is equal to R2, that we can say is equal to some R. Fine. Using these, now our earlier equations will change. So using these equations at delta is equal to dm, equation 1, what it will come? So we will get therefore angle A will be R1 plus R2 which is equal to R, correct? So R plus R, so A will be equal to 2 times R, or we can say small r, that is angle of refraction will be A by 2. Let us call this our third equation. Now using that, that is I equal to E. What will happen to equation number 2? Equation number 2 will become, in place of delta we'll write dm. What is dm? Angle of minimum deviation, which is equal to I plus E. In place of E we can substitute it as I. So I plus I is 2 times I. So 2I minus A, or rearranging you can write therefore I, that is angle of incidence, you can write as A plus dm divided by 2. This we'll call as equation number 4. Okay, so now you are going to make a note of equation number 3. What is 3? Refraction R is equal to A by 2 and incidence I is equal to A plus dm by 2. Now let us find the refractive index of the material of the prism by using Snell's law. So we get n21 refractive index of 2, that is the material of the prism. This will be equal to sine of I by sine of R. Okay, but from equation 3 and 4 we can substitute values for I and R. So we will get therefore the refractive index n21 equal to sine of, how much was I? I was A plus dm by 2 divided by sine of R. How much was R? R was A by 2. This equation, this is known as the prism formula. Okay, so again it is applicable for all types of prism. From the prism formula you can find out, if you know the A, that is the angle of the prism, you have to find the angle of minimum deviation and we will be able to find out the refractive index of the material of prism. Once again, from exam point of view, this derivation is important. Next we are going to talk about optical instruments. Okay, and we are going to discuss two optical instruments. First is the microscope and the other is the telescope. The topics in between about the rainbow formation, scattering and all, now they are not in our syllabus. Okay, so after prism directly you can jump to the optical instruments part. So first, as I said, let us look at the microscope. Now this is a compound microscope. Of course we also have a simple microscope. Simple microscope will consist only of one single convex lens. So if you have a single convex lens, that becomes a simple microscope. But of course for getting higher magnifications we use a compound microscope. Compound microscope makes use of two lenses. One lens is called as the objective and the other is called as eyepiece. How do we understand which is which? The lens that will be closer to the object will be objective, right? And the one that is closer to our eye, from where we are going to look at, that will be the eyepiece. Fine, that is one thing. Another thing to remember, the objective, you will see it has got a smaller aperture as compared to the eyepiece. Eyepiece will have a larger aperture, objective will have smaller aperture in a compound microscope. Okay, now these things are important to understand, because when you are making the diagram, correct, whether the diagram is correct or no will depend upon that fact. So for that is about the construction. Next, FO will be focal length of the objective lens, FE will be focal length of the eyepiece. The distance between second focal length of objective and the first focal length of the eyepiece will be called as tube length or L. Okay, that will be denoting by L. So now what is happening here? This is our object that is having height h. Now h is this will be a smaller object. We want to magnify and see it. So this is going to, the light from this object h will pass from our objective, which will form an image at this point, that is at the focal length of eyepiece. Again, this image will be slightly magnified, but it will still be quite small. So now this image will act as object for our eyepiece, right, which will produce a much magnified image, which will be produced over here like this. Okay, and then when we are looking from the eyepiece, we will be able to see this quite magnified image. Correct? Getting the idea? So once again, the objective forms an image, correct, and the image formed by objective will act as object for the eyepiece, correct, which will form a magnified image. Now of course we can adjust the distance between the eyepiece and the objective to get a proper magnified image. If this is formed exactly on the focal length of eyepiece, the image will be at infinity, which will be magnified, but it might not be so clear to see, correct. So we try to form it at our distance of distinct vision, which is nothing but 25 centimeters. So if image is at a distance of 25 centimeters from your eyes, we are able to see it properly. So we try to form this image between the focal length and the optical center of that eyepiece lens. So somewhere over here we try to form the image from the objective. So we get the image distance, the final image at a distance of capital D, which is 25 centimeters. So with that in mind, now let us do our derivation. So now this object is subtending an angle of beta. This is the angle that is subtended, right? So this is where we will start with our derivation. What do you see? We see that tan of beta will be equal to opposite by adjacent. Opposite here will be h upon adjacent is FO, focal length of objective, which will also be equal to, if you look at this triangle over here, beta will be h dash, that is the image height, divided by the tube length, that is capital L. Or we can rearrange this and write h dash by h will be equal to capital L by FO, which is nothing but the magnification by the objective. So our objective will create a magnification that will be equal to L upon FO, correct? So this is the equation first we will keep in mind. Let us call it equation number 1. So objective is going to form magnification. How much is the magnification? That is tube length divided by focal length of objective. Next we will find magnification by the eyepiece. Now the image by the eyepiece can be at 2 points. Either it can be at infinity or it can be at the distance of distinct vision. So let us do it for when it is at infinity. So if the image is formed at infinity, the magnification by the eyepiece, this will be actually something called as the angular magnification, will be equal to D by FE. What is D? D is the distance of distinct vision, 25 centimeters divided by FE. What is FE? Focal length of the eyepiece. Let us call this equation number 2. So what will be total magnification by our compound microscope? Total magnification will be magnification by objective into magnification by eyepiece, which is equal to, by objective we found out it was equal to L upon FO multiplied by the eyepiece we see it is equal to D upon FE. So this is the formula for magnification by a compound microscope, correct? So I think the derivation is quite simple to understand. All you have to remember is this formula. Now as I said, this will be when image is at infinity. Suppose we are not forming at infinity but at 25 centimeters, then this formula will get replaced by m is equal to 1 plus d by fe. That will only be the change. Otherwise all the other derivation will remain the same. Now that was for compound microscope. Next we are going to see the derivation for a telescope. Now of course we know telescope will use for objects which are very very far away, right? That is objects which are at an infinite distance, right? So what is the difference between a microscope and telescope? This will be the objective and this will be the eyepiece. So here you will notice the objective is having larger aperture, eyepiece is having smaller aperture. Okay, so the situation will be opposite to that of microscope. So objective has got larger aperture, larger focal length. Eyepiece will have smaller aperture, smaller focal length. Fine. Now here we will be arranging them such that the second focal point of the objective and first focal point of eyepiece are going to coincide. So this is the light that is coming from an infinitely far object. So it will be parallel rays. So they will again objective will form the image here at Fe. Correct? It will be a smaller image. This will act as object for the eyepiece, and then we will get a comparatively larger image. Image will be inverted. So in most of the telescopes that you will get, you are having some kind of prism which is going to invert that image again, so that we will be able to see the image right side up, right? So that is the situation for the telescope, and that is the ray diagram. Now how much will be the magnification, right? The magnification that we will get in the case of telescope will be an angular magnification, which will be equal to angle subtended by the image, which is beta, this angle here, beta divided by angle subtended by the object, that is alpha, this angle, correct? So magnification will be beta upon alpha, which will be equal to, now how much is beta? Beta will be again tan of beta you can take as h, opposite upon adjacent. So h upon fe, since beta is very small, so instead of tan, we can directly write it as beta. So tan of beta will be equal to beta. So we can write therefore B is equal to H by Fe divided by alpha. Alpha will be equal to H by Fo. H will get cancelled and then we get M is equal to Fo divided by Fe. So magnification by the telescope will be equal to focal length of objective divided by focal length of eyepiece. So if you want to have a larger magnification, your eyepiece should have a larger, the objective should have a larger focal length, and also the aperture should be large so that maximum light can be captured. This example that we have discussed, this is called as a refracting telescope, where the light is refracted. We also have some telescopes which are called as reflecting telescope, which will have a convex mirror will be fit inside. Okay, so there will be a combination of a concave mirror and a convex mirror that will actually help us to see a more magnified image. Generally, the reflector type telescope, correct? They are actually much more powerful as compared to a refractor type telescopes, right? Because these will have a constraint, correct, with regards to their focal lengths. But a reflector telescope you can make quite large, right? So that is about the microscope and the telescope.